How fast are you moving compared to the universe itself? Could James Webb see the moon landing sites from the Apollo era? And what do I think about smart telescopes? All this and more in this week's question show. Welcome to the question show. Your questions, my answers, as always, wherever you are. Across my channel, if a question pops in your brain, just write it down. I will gather them up and I will answer them here. All right, let's get into the questions. Sod Kyle. We can measure our velocity relative to the Earth, the Moon, the Sun, the Milky Way, but what is the biggest thing we can measure our velocity relative to? And do we know what velocity we are if we are sitting in a chair on Earth? Yeah, you can measure your velocity relative to anything you want. You can measure your velocity relative to the chair you're sitting on and it's 0. You can measure your velocity compared to the space that the Earth is passing through, and you are traveling with the Earth at about 30 kilometers per second. You're rotating on the Earth at about 1,000 kilometers per hour. You're moving with the Milky Way as it is rotating. You're moving with the Milky Way as it's drifting through the universe. And so the largest thing that you can measure your velocity relative to is the cosmic microwave background radiation. And this is the first light that was let out into the universe. And these photons have been traveling for 13.8 billion years. But when astronomers measure this cosmic microwave background radiation, they see a slight blue shift for the half of the sky that the Milky Way is moving towards, and they see a slight red shift for the half of the sky that the Milky Way is moving away from. And they can calculate this and they get about 630 kilometers per second. And so just by sitting in your chair, you are moving 630 kilometers per second compared to the cosmic microwave background radiation. You've probably noticed the Star Trek planet name that appeared above my shoulder in the first question. Of course you did. You're observant that way. This is a way for you to vote to tell us what you thought was the best question of the week. So watch the whole episode, but we will put the names of all of the planets down in the show notes down below. And at the end, just write down that name for the question you thought was the best. We will count up all of the votes and we will celebrate the winner. So this week, the winner was for Rev MSJ, what would be considered an unequivocal biosignature. And I hope you all enjoyed the answer, and thanks everyone who voted. And so vote this week. Captain Dick G's. So wait, we could use James Webb to see the moon landing sites. We know exactly where to look, so why haven't we done this? There's a couple of reasons. One is that you don't want to point James Webb towards the moon. James Webb is an infrared telescope. It has this gigantic sun shield that is underneath it. And the whole purpose of the sun shield is to put it in between the sun and James Webb. And in fact, the orbit that James Webb is at puts the sun, the Earth, and the moon all in roughly the same spot in the sky forever from the perspective of this telescope. And so these three bright infrared objects are hidden to James Webb. The light from the sun has to go through all of these layers of fabric through the sun shield to eventually try to warm up the telescope. And so the last place that anyone using James Webb wants to look is in the direction of the sun. They spent billions of dollars so that it will never have to experience the sun. It is always in the coldest, darkest shadow that they could put together. Could James Webb see the moon landing sites? No, they're too small. But you don't need James Webb to do that. What you need is a spacecraft that is orbiting the moon. And in fact, there is one. NASA's Lunar Reconnaissance Orbiter has been orbiting the moon for well over a decade and flies within just dozens of kilometers of the surface of the moon and has imaged the entire lunar surface down to like less than a meter resolution in some places. It's incredible how much data we have about the surface of the moon. And in 2011, NASA had to change the orbit of the Lunar Reconnaissance Orbiter, and that allowed them to get some even closer shots of the lunar landing sites. And so they were able to come within 22 kilometers of altitude above the moon landing sites. They were able to image each one of the landing sites, all 6 of them. And the resolution, the things they were able to see from the mission are incredible. They could see the lunar landers. They could see like the various experiments that had been set up on the surface of the moon. They could see where the little lunar rover was in the later missions. They could see the footprints of the astronauts as they were walking around on the surface of the moon. And so that is like, those are going to be the best images that we have of the lunar landing sites probably forever. Like unless somebody goes back and actually revisits the sites, images from orbit they're just amazing. Boboblio 4002. The moon regolith is known to be really rough on space equipment, plants, and lungs. Is there some kind of device like a rock polisher that could be used to make it safer for things like plants? Yeah, you're exactly right that the regolith on the moon is a very hazardous substance. What it is the pulverized volcanic rock left over after billions of years of meteorites of varying sizes have smashed into the surface of the moon and just broke it up into smaller and smaller pieces. Now, we have similar material here on Earth, pieces of sand, things like that. And you even have this on Mars, that you've got the pulverized fragments of volcanic rock on the surface of Mars. But the difference is here on Earth, we have wind and water erosion. On Mars, you have wind erosion that sort of takes these jagged pieces of volcanic rock and sort of wears the edges off of them. But on the moon, there is no erosion. And so all of this stuff is sort of in its perfect, sharp little jagged state. And when the astronauts went to the moon, they realized that this stuff is a lot trickier than anyone had ever anticipated. You see pictures of the astronauts, and they weren't out for very long, and they are just covered in this dusting of this regolith. They found that they were immediately getting irritation in their lungs when they were breathing it in. It caused irritation in their eyes. Now, the good news is there was no long-term problem for the Apollo astronauts for the short amount of exposure that they had to this regolith. But we know that there are substances that are very similar, like asbestos and other things, that will cause very long-term damage to astronauts. So like just dealing with the regolith, keeping this regolith out of the habitat is going to be really, really important. But the point you're making is, well, what about plants? Like, aren't we going to want to grow stuff in plants? In fact, a bunch of experiments have been done here on Earth where people have tried to grow plants in both simulated lunar regolith and actual lunar regolith. And they found that it works, but the regolith has no organic material in it. And so the plants will sprout, they'll grow for a little bit. In other words, like the roots can grab on to the parts of the regolith, but it's not actually deriving any nutrients from it. And so the plants will sprout up and then they'll die because there's nothing to go with. But it didn't seem like it was a problem for like the jagged shape of the regolith. And if anything, the plants are going to act like a form of erosion. And so if you did bring in some regolith, mixed in a bunch of organic material, made it wet, planted plants in it, then you're going to find the stuff is going to get safer and safer over time. That said, like if you bring this stuff in and you're gardening in it, then it's going to kick up dust. The dust is going to go into your lungs. The dust is going to go into your eyes, and that's going to be a problem. And so you're exactly right that probably the solution is to, when you're going to bring in the regolith from outside, you're going to mix it in some kind of water solution. Either just mix it up for a long time until it wears down a little bit, or maybe you're going to put in some kind of material that it's going to rub against, that's going to help take off the rough edges and smooth the stuff out. But you do not want to have clouds of lunar regolith inside your research facility for any length of time. And this right now is probably the largest unsolved problem in having people be on the moon. I mean, we know how to deal with radiation, stay underground, the low gravity. I mean, don't stay there for very long. Temperature, pressure, power is going to be issues. But how do we deal with the wear and tear on every piece of equipment that's going to be experienced by, thanks to this lunar regolith? We still don't know what the solution to this is. L. John Keller II. Do you think that all-in-one smart telescopes like C-Star, Dwarf 2, Vaonis, Unistellar, and so on are the future of amateur astronomy or a passing fad? So I've had a chance to use one of these, which was the Vaonis telescope, and it was amazing. Like, these smart telescopes feel like magic. You take the telescope, you put it down, you pair it with your phone, it looks up into the sky, it knows where it is from your GPS, it plate solves some stars on the sky, uses that to figure out what part of the sky it's looking at, and then you just say, I want a picture of Andromeda, I want a picture of M33, whatever. And it just goes ahead and gathers pictures. It uses like Instead of it being like a telescope you can look through, it has a camera that actually records images and then stacks them up the way astrophotographers do. And even in light polluted skies with one of these telescopes, you can take pictures of the night sky. So they're absolutely not a fad. And I think, some of the fundamental technologies that have been incorporated into them just solve some of the greatest problems that anyone who has owned a previous generation of telescope has dealt with. And that is that these things are so hard to align that if you have a manual telescope like a Dobsonian, it's great, you point at a thing in the sky, but if you don't know where the thing is, then you're going to want some kind of go-to mount. But the go-to mounts, you can spend half an hour, or forever attempting to polar align your telescope and never get it lined up perfectly. And so you got friends come over and like, oh, there's Jupiter. Let's take a look at Jupiter. Okay, fine. You're going to spend all this time. I'm almost there. Why doesn't this work? It's awful. But these smart telescopes, they just take all that problem and just make it go away. The ability to be able to just let anybody do astrophotography is fantastic. So I think these are all definitely on the upsides. So here's the downsides that I think so far. The first one is these things are expensive. Like, some are cheaper, some are more expensive, but you are looking at, compared to a traditional go-to telescope, you're looking at a lot more money. And they have nice optics, they have a nice camera system in them, but they also have all this additional intelligence and robotics that makes the telescope work. And so just kind of size for size, you could spend more money directly and buy a nice telescope, a nice camera system, a really good mount, and you're going to be able to take better pictures. They're going to give you more control over it. And then the other thing is, like, they're not great for doing visual astronomy. You can do it, like you can go, hey, let's take a look at Jupiter, and then you can point at Jupiter and bring up pictures of Jupiter, but you're not looking through the eyepiece. And so if that's really important to you, then I think that's the thing you're going to want. I think the future of astronomy, of this technology, is to make the plate solving part, the simplicity of the go-to, what technology needs to exist in every future telescope from here on out. And it's sort of like the idea that I've always had is that you would have a mount that has its own little telescope on board. And all the mount does is looks around at the sky, finds the stars that it recognizes, and knows where it is and what it's looking at. And then you can put any kind of telescope on top of it, and then you can kind of get the best of both worlds. And, I'm sure people have already come out with this version of a mount so far. So, they always say, like, the best camera is the one that you actually have with you. And I think in astronomy, if you want to take pictures of the sky, like, the best telescope is going to be the one that you're willing to use quickly. And if you find you've been struggling with the go-to telescopes in the past, these things are fast. You set it up, you're taking pictures, you're having a good time. And so I think that goes a long way for them. So I think they are the future. I think we're in the initial stages of this, but I think we're going to see some version of this technology in every major consumer telescope into the future. Briscoe Rob, when is the universe expected to bounce back like an elastic band? Well, we don't know what the future holds for the universe. One of the big questions that astronomers have been asking is, what is the fate of the universe? How will it all end? And so one possibility is that the universe is expanding, and then it's just will slow down over time and eventually coast to a stop. Another possibility is it'll slow down over time, but it'll never reach sort of the stopping point. And the other possibility is that it will slow down over time, and then the mutual gravity of all of the galaxies will pull it all back together again, and then you will get this, as you said, this sort of elastic band rebounce. And so everything would sort of run in reverse. Temperatures would get hotter and hotter and hotter, and eventually you get some version of another Big Bang, or maybe it just smushed together again. And this is called the Big Crunch. And so back in 1998, astronomers wanted to find out what was going to happen. And so they used this cosmic yardstick of type 1a supernova, which are a kind of supernova that explode with exactly the same amount of energy. When you measure the brightness of one of these supernova, then you know how far away it is because you know how much energy was in the explosion. And they did this really precise measurement of all these supernovae. They wanted to know, is it going to crunch back together? Is it going to slow down and just reach a stop at infinity time? Or is it just going to keep expanding forever? And what they found was that, in fact, the expansion of the universe is accelerating. So it's doing none of those three things that they were expecting. It's actually getting the separation between galaxies is growing and accelerating over time. And this is dark energy. This is this discovery, this observation that the universe is accelerating. And so now it's not expected that the universe will ever collapse back down and like an elastic band, that it will continue to expand, that it will get less dense over time. Eventually, all of the galaxies will run out of gas, all the stars will die, the black holes will evaporate away, and the entire universe will cool down to some just average temperature. And this is known as the heat death of the universe. And this is the way the universe is expected to end. Indoor teacher, what are your thoughts on the samples from OSIRIS-REx? So the OSIRIS-REx mission has a special place in my heart because I watched the rocket launch. When you go onto my channel, the introductory video is me and my wife and Chad going to Cape Canaveral to actually watch the OSIRIS-REx mission launch. It was amazing. First and only time I've ever seen a rocket launch. And now here we are at pretty much the end of the mission part where the samples have been returned to Earth, and they've been able to finally get the sample capsule open and be able to distribute them around the world. And the plan was that they were going to get about 60 grams of material from asteroid Bennu. And in reality, they got about 250 grams of material. And so there's so much material. They're going to be able to distribute this to various labs around the world. They're going to be able to put this into museums at the Smithsonian. When I was in Tucson about 2 months ago, there was a whole exhibit where they were going to show you samples from OSIRIS-REx, but they hadn't been able to get the sample capsule open. And so there was like sample goes here, and at the it was at the Gem and Mineral Museum in Tucson. So I missed getting a chance to actually see them up close. So it's too early right now because they just got the samples open and they've just handed them off to various researchers. But we're about to witness the power of Earth's labs, where you've got scientists here on planet Earth with the best facilities at their disposal to be able to study pieces of an asteroid. This is like, people always ask me, like, why bother bringing samples back to Earth when we can go to another world? We can take a rover like Perseverance. It can carry a microscope and other stuff on board. But a tiny little miniaturized mass spectrometer just does not compare to a facility that is as big as a lab here on Earth, with scientists able to work with samples, be able to modify and change, try different experiments. It's the scale of this is so much bigger. And so, it's so early right now, but like some of the initial ideas, I heard a quote from Dante Loretta. He's the principal investigator of OSIRIS-REx, that he thinks, based on the kinds of samples that they're seeing, that this might have been exposed to water in the past. And so maybe this was part of Earth, or some part of something that had water on the surface in the ancient past. And that would just be mind-blowing if that's true. So that would tell us about the early solar system in ways that we just never knew. So we are just in the early stages of this. And over the next couple of years, we're going to hear paper after paper after paper where people are announcing the things they found in the OSIRIS-REx samples. And then you take that idea and then you think about what is going to happen when we get our hands on the Mars sample. Like, it's one thing to have Curiosity and Perseverance rolling around on the surface of Mars, drilling into the rock and doing the best that they can, and to have those samples back here on Earth in the hands of scientists doing really deep science work on the samples. So I can't wait to hear the science from OSIRIS-REx, and I really can't wait for someone to bring some samples home from Mars. Abdallah, what is dark matter? Nobody has any idea. Astronomers can observe the effects of dark matter. They can observe how its gravity influences the motions of stars, how it distorts light, how it changes the way stars rotate inside galaxies, its influence in the cosmic microwave background radiation. Astronomers can see how blobs of dark matter are orbiting around galaxies. They can see galaxies that have only dark matter, galaxies that have no dark matter in them, and places where dark matter has been stripped away from the gas and dust. What is it? Nobody knows. Roadside rebels. Even with the damage to the helicopter on Mars, have they tried to fly it or just too much vibration, etc.? Yeah, from everything I've heard from NASA is that the mission is over. They're not going to try to fly it. They're done. And I think you've got always this balance. Do you want to push your technology to one final step to see what's going to happen? Right now, it's sitting safely on the surface of Mars. Maybe some future explorers are going to be able to come and find it and to be able to analyze the material on it. Perseverance can't stick around and I don't know, pick it up every time it knocks itself over on its side. Perseverance has work to do. And so it has to leave it alone now sitting on the sand dune. So NASA, looking at the damage to the rotors, decided it was unsafe to fly. This is the end of the mission. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Lee End, Ryan, Benjamin Mueller, Tim Epperson, Sean Drummond, Trevor Stack, Sycom Nelson, Aaron Gabor, Zaxtel, Chris Rote, Philip, and Frederick Wydron. Join the club at patreon.com/universetoday. Jesse Hardy, I heard scientists say that all of the planets around TRAPPIST-1 system might have lost their atmospheres a long time ago. Have you heard this? Yeah, not only have I heard this, but I suspect you read this article on Universe Today or one of the websites that reprints Universe Today stories. Maybe phys.org. I believe the title that I came up with was, if there are any atmospheres at the TRAPPIST-1 planets, they're going to be long gone. And astronomers looked at the amount of radiation that's coming from the TRAPPIST-1 star, considered if there were atmospheres around the planets, ran a simulation, and found that within about 100 million years or so, all the atmospheres of all of the TRAPPIST-1 planets should have been stripped away. Is this the final answer? No. I mean, you need to have James Webb actually make those observations of the atmospheres around the planets at TRAPPIST-1, and also make tens of observations on other planets around other red dwarfs before we can start to really rule out this idea that red dwarf planets can have atmospheres at all. Right now, things are looking great. We know that there's no atmosphere around the first two planets orbiting around the TRAPPIST-1 star. There was another red dwarf star with a planet that has been determined that it doesn't have an atmosphere either. And so we're waiting for the rest of the TRAPPIST-1 planets. But I would not be surprised if TRAPPIST-1, D, E, F, all of them have no atmospheres. And if we get to a point where we've seen several dozen planets having no atmospheres around red dwarf stars, then I think at this point astronomers are going to say, okay, we can't look for life around red dwarf stars. It's too early right now. We're still in this sort of in-between stage where we don't know and we're hopeful, but don't get your hopes up. Jesus Solus. If satellites are the first products being used to build a space economy, what would be the next product? Is there anything specific that you're interested in seeing while a space economy develops? That's a really interesting question. And I think this sort of leads on to the interview that I did with Zach and Kelly Weinersmith about how ideas for a city on Mars or on the moon or things like that are very far-fetched. We absolutely know that satellites are a profitable business. Starlink is going to make so much money. There's tons and tons. Weather satellites, Earth observation satellites, communication satellites, navigation satellites. There's all kinds of money-making reasons why you would put satellites in orbit around the Earth. But then what comes next? And that's a really interesting question. When you think about all of the ideas that Zach and Kelly analyzed, none of them really seem to make any sense. Like space power, probably infeasible. Asteroid mining, unfeasible for a long time. Space-based manufacturing, we can manufacture stuff down on the Earth. So space tourism, there's only so many billionaires on Earth who are going to want to go and float around in zero gravity, and they won't be able to bring the prices down for regular people to be able to do it for a long time. So that sort of taps out at a few thousand people a year. What's next in space? And I don't know. So what I think that we will see is that we will see things like, say, the Deep Space Gateway, and we will eventually see a lunar base set up by NASA, or maybe an international collaboration, or the Chinese. There will eventually be multiple lunar bases, and they're going to require supplies. They're going to require water and other stuff. And so maybe there will be commercial contracts for partners to be able to bring material to these lunar bases to keep everybody alive. There will be commercial contracts to send supplies to and from the moon. But I can't think of reasons beyond that. And so I guess infrastructure, if I was just to like put a catch-all term, it would just be infrastructure. There will be telecommunications relay satellites farther out in the Earth-Moon area. There will be asteroid mining, maybe to bring supplies to the Moon Research Station. So it's going to be like supplies for whatever stuff that we have in space. So I'm going to call it infrastructure, but it's going to be not very much for a long period of time. And I know that's not the science fiction future we were all hoping to hear, We want to be able to hop into our starships and fly from world to world and get off and, hang out under alien skies. But yeah, I just don't see a lot of things that are going to make us money in the medium term. Chaos scientist or rapper. If we set off an ungodly amount of explosives on the moon, could we create a pseudo atmosphere? Because we could then start some kind of erosion, no? Yeah. So I'm not sure about setting off a bunch of explosions on the moon. Like if you set up a bunch of bombs on the moon and you exploded it, then you would create this giant cloud of regolith around the moon. In fact, like when a rocket lands on the surface of the moon, the dust that it kicks up goes into orbit around the moon. It can actually be damaging for any spacecraft that's going to attempt to land on the moon. You got to wait for that dust to settle back down before you attempt to land on the moon. So that sounds dangerous, but, and I love this, that you could take like a comet or something and you could supply atmosphere to the moon, with magic, who knows how. And you could build up an Earth's atmosphere worth of just air at the moon. And that would last for about 10,000 years. So, every few thousand years, you would have to then top it up a little bit, which, I'm sure it's a ludicrous amount, and who knows if we'll ever do something like that. But wouldn't that be so amazing that we would have the Earth with its atmosphere and oceans and all of that, and then you could have the moon with its own oceans and atmosphere. Like as long as you keep that thick atmosphere, then the place is going to be great. And you're exactly right. You would get erosion. Now it would be weird because like a day is 14 days long and a night is 14 days long. And so it would be very cold on the far side. Like it would be still a weird place to go. But, once you got an atmosphere set up at the moon, it would last for a long, long time, for as long as like human society has been around. So people always ask me like, where should we terraform first? And my answer is always the moon. Sid Vicious, how can we trust the achievements of the Chinese space program and their contribution to the scientific community if their space program and that is tied to the CCP government, which we can't trust? That's a tricky question. On the one hand, you have the Chinese government. And, I'll let you run whatever narrative in your brain you want about the Chinese government right now. But, I know the things that you're going to say. And then on the other hand, you have real things that are happening with China. They've landed on the moon many times. They've returned samples from the surface of the moon. They've landed spacecraft onto the surface of Mars. They are planning now to have humans set foot on the moon, probably 2029. Like, we're about 5 years away from the Chinese actually setting foot on the moon. And their plan is then to follow on with that with some kind of permanent base. All of this technology that's gone into sending humans to the surface of the moon, the plan is to send them to the surface of Mars as well, probably in the 2030s, 2040s. And all of the work that they're doing is proceeding according to schedule. They're hitting all of their deadlines. You're not hearing about the budgetary cuts that are happening in the US. You're not seeing the kinds of delays that are happening with other space programs. They have the world's largest radio telescope, which is with the FAST telescope. It's 500 meters across. They're building the world's largest steerable radio telescope. They're building a Hubble-class space telescope that they're going to be able to operate near the Chinese space station. They're developing a giant neutrino detector in the Pacific Ocean. They are working on some really interesting cutting-edge gravitational wave observatories, both ground-based and space-based, including like an interferometer that would work similar to the way Lisa does. And it's not a completely separate world here. You have these collaborations. They're, if you're an astronomer that works in Europe or in Canada, or even in the US, but you don't have, say, directly government funding, you can get time on, say, the Chinese FAST telescope, and you can do collaborations with Chinese astronomers. There are tons and tons of papers, of research papers that I see every day in archive and various prepresses and journals, which are a collaboration between Western scientists and Chinese scientists. So there's a lot of collaboration and cooperation that is going on. The best thing to do is for people to work out ways to work together, to peacefully collaborate for the betterment of humanity. And that's going to require negotiation. That's going to require willingness to work across borders to figure out ways that you can improve our scientific understanding together. And I think that people hold these just black and white views about things. And I don't think it's realistic. Like, I think, you could have problems with a country's government, but you would have no problem with the people. You would love to spend time with the people, and they would be warm and caring and let you into their home and show you the utmost hospitality. And that's the kind of experience that you would probably have with the researchers if you're collaborating on projects together. So it's complicated, and I don't know what the answer is. I'm just a journalist. I will tell you what projects are being worked on in China as soon as I hear about them, as soon as they inform they lift the veil of secrecy and tell us what's going on. And I'll also tell you what's going on in other countries as well. And I don't think there's any simple way to proceed that isn't nuanced. Toomby, what are the chances that dark matter is just gas and dust that we can't see? Almost zero. Like, if you take the mass of a galaxy, like the Milky Way, and then you multiply it by 10 so that you account for the dark matter that is interacting. And when you think about how we can look in the galaxy and we can see the reserves of gas and dust, we can actually measure the signal that's coming from gas and dust. How could there be 10 times as much gas and dust in the Milky Way than what we can see when we can see gas and dust? So you can pretty much rule out that it's gas and dust. And we know that when gas and dust, especially one that is 10 times the amount of the mass than of the stars, it would interact in ways that would heat up, it would glow, we would detect it in X-rays and a lot of different wavelengths, and we don't see that at all. And I don't know why, but people really are bothered by this idea that there is an invisible particle that we can't see. But we've been through this before. The neutrino. When scientists looked at the fusion that was going on inside the sun, they made the calculation to say, well, if this is what's happening with the fusion, there is this tiny remainders worth of particles that must be getting out into the universe, and that we don't detect them. We can't see them with our telescopes, so they must not interact. And yet there has to be a lot of them that are coming from the sun. And so then they had to create these gigantic detectors of like enormous amounts of water. And then they would get like one interaction between a neutrino and one atom in this enormous swimming pool's worth of water every, I don't know, long amount of time. And from that, they were able to calculate that, yes, indeed, the neutrino exists. And yet a neutrino, I've said many times, you can have a neutrino go through a light year's worth of lead and not interact with a single atom of lead. Like, that's how little neutrinos interact with the rest of matter in the universe. And we can't see them. We don't see the light. And so, we know that neutrinos are there. We know they're real. In fact, it's kind of amazing. Astronomers have used the Ice Cube telescope in Antarctica to make an all-sky image in neutrinos. You can actually see the Milky Way because of this image in just neutrinos. And obviously the brightest signal in neutrinos is coming from the sun, but neutrinos have been detected coming from supernovae. So we've gone through this process before where there are particles that don't interact with regular matter that are incredibly difficult to detect. It just seems that dark matter is even harder, but it's there, whatever it is, or it's not there, and we just don't understand gravity at the largest scales, which is also fine. Either of those is just, or it's black holes, which would be even cooler. So, but yeah, we know that dark matter isn't the things that we know how to see. Sure, Mark. Will the public be informed if JWST suffers more damage? Of course. Astronomers who are using JWST need to know what are the capabilities of the instrument at all times. And so every time there is an impact on JWST from a micrometeorite, then information is relayed around inside the agency. It's publicly available. We know exactly how many impacts have happened so far, on which panels they've happened, the severity of the impact, probably the size of the particle. I could, as a journalist, or you could as well, contact NASA and find out what the current state of that is. And they have no reason to hide it, because any astronomer who uses Webb and is expecting a certain capability out of the instrument and then notices that it is not delivering that capability is going to wonder what the problem is. And they're going to have to explain that it was damaged. Well, so you just explain that it's been damaged. So yes, I don't understand why people think that there would be some kind of secrecy. And also, it's not like astronomers are like all work for NASA. Very few astronomers work for NASA. Astronomers work all over the world for thousands of different organizations, for research universities, for space agencies, for private companies, all kinds of things. And they are all working in their own way, observing the sky. It's kind of like if a bunch of people in a city decided to buy new cars, would the car companies inform the public? Like, the people who bought the new cars are going to inform the public. They're going to tell their friends they bought a new car. Like, that information is just out in a million different ways. So there's no way to there's no central authority that is controlling it. And that's the way astronomers work. And in fact, astronomers won't shut up about the things they've found all the time. The instant anybody finds anything, they're contacting their colleagues. They are posting papers in journals. It doesn't go anywhere near the government at all. Like you get a private, say, like a university, say a Harvard. Harvard has an astronomer. The astronomer books time on a telescope run by the European Southern Observatory. So it's a European collaboration. The telescope's located in Chile and the astronomer is in Boston. And then they discover a new kind of supernova, and then they write up their paper, and then they put it out on the internet immediately. And then they submit that paper to a journal that is operated out of England, right? It's like this complex web of interactions. There's no sort of single party that's able to suppress anything. So yes, if life was found in the universe, the public would be informed. If an asteroid was inbound to Earth, the public would be informed. And if there's any damage done to James Webb, the public would be informed, because it'll just leak out from every orifice. JLab-63, is a nuclear ion engine a thing? Can it be a thing, or are they separate? Nuclear, thermal, and ion engine. Yeah, a nuclear ion engine is theoretically a thing, and you're right, they are separate things. So on the one hand, you have a nuclear reactor, some kind of fission reactor that is putting out kilowatts of electrical energy. And then you have an ion engine, and the ion engine is using electrical energy to accelerate some kind of propellant up to high speeds, and they use that for propulsion. And so normally ion engines are limited by the amount of electricity they can get, the size of the solar panels. And so they're incredibly efficient, but they don't put out a lot of thrust because you've got solar panels, maybe you're getting a couple of 100 watts of energy that you're using, you're accelerating ions magnetically out the back of the spacecraft, you don't get a lot of thrust. But if you put a nuclear fission reactor onto your spacecraft and it is generating kilowatts of electricity, you can have fission reactors that are 100 kilowatts, 400 kilowatts, just like orders of magnitude more electricity than you would have from solar panels. And so you can have bigger ion engines, they can produce more thrust, you can have multiple ion engines, and you get a much more change in velocity. So there have been some missions in the past that considered this idea. There was an idea for sending a mission that could fly to all of the moons of Jupiter, could just go into orbit around each one, analyze the moon for a while, fly out, go to the next one, analyze the moon, fly out, go to the next one. And it would have used this idea of having a fission reactor bolted on with an ion engine. And I can't wait to see if somebody, like if we do get a nuclear rocket in space, I would love to also see some kind of nuclear ion engine rocket. All right, those are all the questions that we had this week. Thank you everyone who asked questions in the YouTube comments, as well as everybody who showed up for the live show. We do the show every Monday at 5 p.m. Pacific time. So if you want to see the full 2-hour live question show, come join us every Monday. There's going to be a reminder somewhere here on the channel, so you can click to remind yourself when it's going to get started, and you'll get an email notification from YouTube, and you can show up and join it. So last week, I asked you to provide me with recommendations for YouTubers who are doing a great job of science communication, space science communication, and I'm still waiting for all of those because you haven't heard about it yet, but you will this week. So I'm going to provide another recommendation to you for a small channel that you should check out. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Antonio Lofilara, David Giltanan, Dougie Stewart, Dustin Cable, George, Jeremy Mattern, Jordan Young, Josh Schultz, Mark Anastas, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other patrons. All your support means the universe to us. All right, so another recommendation for a small YouTuber, and at the time that I'm recording, she only has 8,380 subscribers on YouTube, and that is Dr. Maggie Lieu. Her handle is SpaceMog, and she's an astrophysicist who works at the University of Nottingham. She specializes in dark energy, but has a really great knowledge of all things space and astronomy. And I've done collaborations with Dr. Lieu several times in the past. She's a terrific guest, can sort of answer any questions that I have about dark energy. And I do not understand why she doesn't have like a lot more subscribers. So if you want a channel for somebody who actually researches this stuff directly, I highly recommend you check out Maggie's channel. She's fantastic. So again, please let me know. I want to find channels that have less than 10,000 subscribers who you think do a really great job of accurately reporting space and astronomy information, conveying it, educational, whatever. I'm trying to provide a great list of people so you can know who you can trust. And so far, these are people that I feel that I can trust. All right, we'll see you next week.